Oh, hello there. Hey guys, what's going on? Memes here. Yes, we have returned. And yes, as we can see, this is an entry into Kurt Mungel's Core 1 contest. Yes, it's right over there. And what we're going to be discussing is units, aka the 5 ingredients of reality as we know it. And part of this was actually instantiated because I had the benefit last year to attend the Wolfram Summer School and do some work on the history of units, as well as make a crazy attempt to try to more formalize units within the Wolfram Physics project because, well, they had an initial methodology and nobody really had touched it since. So did a little work, had some surprising results that are very dubious, full disclosure, but we're going to today be going through a bit of the history of units as well as how they work within physics as we know it. And the goal here is to go through some of the history and help the viewer gain perspective, or perhaps intuition may be a better word for what the heck is actually going on. Because one of the surprising things is when I had given a little presentation, there were some folks that actually had worked as physicists and stuff, and everybody has their own particular discipline and function and everything. But a lot of folks don't necessarily seem to be aware that even though SI has 7 base units, I claim we can computationally reduce them down to 5. And we'll go all through that now, and yeah, hope you all enjoy. So fundamentally, the claim is that within all the different units, and if you go on Wolfram Alpha, you'll find that we have upwards of like 10,000 different units, things that I did not even know existed. However, I had learned from Thad Roberts of the Physics Monastery that we can reduce our dimensions of measure down to 5. Coincidentally, that involves 5 constants of nature, which we can see here. Big G, the Newtonian gravitational constant. H bar, Planck's reduced constant. C, the speed of light in the vacuum. Epsilon naught, the electric constant. And Boltzmann's constant here. And as we can see, these have physical dimensions of measure. You can see here for big G, what are our dimensions? We have a length cubed, so a volume, and it's divided by a mass and then time squared. Cool. We've got H bar here, which is a mass times a length squared, so an area, divided by a unit of time. We get C, the speed of light, is a length divided by the time, because it's speed, of course. We have epsilon naught, the electric constant. Here's where we start getting, you're like, I don't know what's going on. It's like, it's time squared times charge squared, and then divided by a mass and a length cubed, so a volume. Cool. And we got Boltzmann's constant here. This is a mass times a length squared, so again, we got an area divided by time squared, and then a temperature. For those astute viewers, one may notice Boltzmann's constant here, we've got a mass times a length squared divided by a time squared. Wait a second. That sounds like mass times energy. Oh, that's because what it is. And then it's divided by temperature. Okay. So within these dimensions of measure, we can then formulate 5 Planck units. Those Planck units are the Planck time. So we got a notion of time. We got the Planck length. Got a notion of length or distance. We got the Planck mass, which is a notion of mass. The physical stuff, whatever that may or may not be. And then we got the Planck charge over here. So we have a notion of electric charge. And then we have the Planck temperature. So we have a notion of temperature. And we're going to be going through these in much, much more detail aside from just a little board thing. But we'll get into the board exercise because I ended up kind of writing a computational essay because that seemed to be the best way to present things, and I'd kind of already done this at the Wolfram Summer School last year, so I digress. So as we can see here, within these Planck units, by their definition, they use these constants to define them. So basically we use big G, H bar, C, epsilon naught, and K sub B. All right. So the Planck time, what is that? Now, if we notice, one of the interesting things you take away from these Planck units, they're all square roots. That means whatever we are dimensionally getting out before the square root is that dimension of measure squared. I'm just going to point that out. So for the Planck time, what do we got? We've got the square root of big G times H bar divided by the speed of light to the 5th power. So the Planck length is the exact same construction, the square root of big G times H bar, except we're dividing by the speed of light to the 3rd power. The Planck mass is a similar setup. We've got the square root of big G, H bar, and we're dividing by C. So we're just arranging those in that particular way, and we get out the Planck mass. The Planck charge is the square root of 4 pi, H bar, C the speed of light, and the electric constant. Note, some folks may use a different convention, and they get that 4 pi out. We're going to go over in probably the next 30 minutes or so my argument for why we should include the 4 pi. Because long story short is the gravitational constant and the Planck charge, they have a very similar construction. You may have heard of that whole mass 1 times mass 2 divided by your r squared, so you get an inverse square law. And for Coulomb's constant, you've got charge 1 times charge 2 divided by r squared. Long story short is they unite at the Planck force. So that's my claim for you doing that. And then we have the Planck temperature here, which is a bit different. We got the square root of h bar times the speed of light to the 5th power divided by big G and then Boltzmann's constant squared. Boltzmann's constant has temperature in it. So if temperature is in the denominator there, this is one of the things we're going to go over, is if we're now dividing that, that puts in the numerator. We've got it squared, so we're going to get 2 dimensions of temperature out. Therefore, we get the Planck temperature. Cool. Is everything crystal clear? Because if it is, that's actually kind of surprising, because this stuff has confused me for a while, and it still confuses me. And one of the reasons for doing this is to better get an understanding for what is going on to the best of our knowledge, utilizing our modern tools, techniques, and maybe a wee bit of numerology, because occasionally that may have worked in the past, but caution. Numerology is just numerology until it can explain more with less. You're also going to want to have a coherent framework, but we're going to have to get into the essay for that. So let's do that now. All right. The 5 ingredients to reality, hashtag core 1. What are we talking about? So basically, within universe, or our world as we know it, we seem to have all these different stuff doing different things.
You got stuff and you got things you can do with the stuff.
That's going to be a reoccurring topic in this discussion here. So the claim is, no matter what the underlying rule of reality may or may not be, my general gut feeling, and this is kind of something I learned from Stephen Wolfram, is that there likely are some underlying simple rules. Now, we might not know precisely what they are, but that's the goal of science, because we want to figure out what's going on. And if we have a framework that kind of works and everything, because, for example, quantum mechanics or quantum field theory has been evaluated to about 14 significant digits. You have the anomalous magnetic moment of the electron. We have general relativity that, according to Sir Roger Penrose, has a precision of approximately 14 significant digits. So there are some aspects that do seem to line up. Now, we have yet to be able to unite them. Now, perhaps some formulation exists. Now, it doesn't seem to be widely known, and it still seems to be a major problem within physics. So the goal here is to attempt to arm the viewer or the reader, because I'm going to include this computational essay, on some of the history of units, kind of like how we got here, because another thing I've learned from Stephen Wolfram is understanding the history from whence we came might actually inform how we proceed in the future. Because if you made mistakes in the past, it's, well, the whole goal of science is to be less wrong, so we can cast aside our misconceptions and figuring out what's going on. I ask that very often. Okay, so long story short is, to my knowledge, and I haven't heard many other folks discuss this, it's as we saw on the board, we can computationally reduce all the different dimensions of measure down to 5 utilizing these 5 constants here. Newtonian gravitational constant big G, the reduced Planck's constant h bar, the speed of light in a vacuum, C, the electric constant epsilon naught, and Boltzmann's constant K. That should probably be K sub B for clarification. These are the values in SI according to some of our best measurements. G is, that's a tough one. That's a tough one. So we've got some new measurements, but we only really have it to about 5-ish digits or so. And that is basically the limiting factor on the value of the Planck constants that we end up getting out. Because anything with big G, you're going to be limited by our precision. So as we can see here, we got this value here, and you see all these units and everything, and these are in the standard units. You got like meters squared times newtons divided by kgs. What the heck is that? And then you've got the h bar, which is joule seconds. What the heck does that mean? Okay, you got c, the speed of light. We should also note that right now 3 of these constants, h bar, c, and Boltzmann's constants, they are defined. I believe Boltzmann's constant is defined, at least Planck's constant and the speed of light are defined by the 2019 redefinition of SI. Okay. So and then we see an electric constant, farads divided by meters. I'm not going to lie. I'm not an electrical engineer. I don't know what that is off the top of my head. We got joules per Kelvin for Boltzmann's constant. So as we were discussing a little bit before, if we look on the board, we could see that it was mass times speed squared divided by temperature. So that's what it's explicitly stating here. So I'm not sure why I have h bar there. Need to correct that, but as we can see here, from these 5 constants, we can generate Planck units. And these are Planck units, and we'll go over a little bit of some of the work that I did in the Wolfram Summer School last year. And again, it's highly speculative, but using an educated guess and or what seemed to be the most logical thing to fit the data, we managed to be able to replicate the initial physics project estimates within about 1 magnitude. The reason why deviates so much from the initial method of calculation, we'll get to that, because the implications, if there were any, are kind of fascinating. But you're gonna have to go through the slog, or at least click to a timestamp to get to that point. So, okay. So as we can see here, now you could do something slightly different. Do you need to specifically use these constants? To be fair, you could swap out the speed of light with a magnetic constant, because by definition, 1 over the square root of the electric constant times the magnetic constant gives us the speed of light. Congratulations. We discovered what Maxwell figured out over 150 years ago. But I know at least me personally, I had originally, now you kind of hear that, but it's like you can go onto Wolfram Alpha, you can use a Mathematica notebook if you want. Personally, Wolfram Alpha is free. It's a website you can go to, and I personally think it is one of the greatest tools ever given to humanity, because it's not just a calculator that accounts for dimensions and everything, but it can also show you the relationships between stuff that you didn't even know existed. So again, I was just playing around. Oh, electric constant, magnetic constant. Oh, what's one over this? Oh, that kind of looks like a numerical value that I recognize. And it's, oh, look, it's speed squared. And again, that's nothing new, but just going through the exercise, seeing this relates to this, this relates to this. You can take the square root, you can invert it, and just the ability to do symbolic manipulation is a superpower, I would claim. Okay. But aside from blathering over how much I enjoy the Wolfram language, again, not a paid spokesperson at this point yet, let us continue here. So essentially, the core idea is that from all our different measurements, from all our different constants of nature, we can boil them down to 5 dimensions of measure: time, space, charge, mass, and temperature. So those 5 dimensions of measure, and what does that mean? I'm not an experimentalist, but we have some measurement. Maybe we apply a conversion. Our detector goes click. Our detector goes click, assuming reality is real and we are actually measuring something, we get an output. But within all the parameterization, at least everything that appears on CoData, you can manipulate them with those 5 particular dimensions. So what we're going to do is we're going to go over a brief history of units. A lot of this is from the linked Wolfram Summer School project. They've renamed the Wolfram Summer School the Summer Research Institute. But as you can see, we're over there. Yes, Matthew Fox is my name. Hey, people, you can call me whatever you want. Don't call me late for dinner. And then the presentation is over here at the Wolfram Institute from a live stream over this past year. Okay, so what we're going to do is we're going to go over a history of units utilizing the 7 base units of SI. So a lot of this is out of this notebook. It's been slightly reformulated. So as we can see here, yes, I enjoy saying click. Basically, before we had all our fancy detectors that go click and everything, we human beings, we were very industrious in everything. So let's say you need to build something. You need a reference if you want things to kind of be about the same. So originally, a unit of length, we used the cubit, which is basically the length of the forearm to your fingers. Because once you happen to be a grown adult, for the most part, probably not going to change that much, or at least a noticeable amount. So if you're working on a farm, you're building a structure or something using your own physical labor, your personal cubit is probably a decent unit of measure. It's a rough standard. Now, one of the problems you run into is, well, human beings, we're all more similar than we are different, but we are all different. So we need to keep that in, or take that, so to speak, into consideration. And while they would do different qubits, like sometimes you'd have the royal qubit and stuff, so you would take the leader's forearm and stuff, and then you would develop a rod and everything. The problem is, once you had a new reagent, that would change. So one of the driving factors, I would love to say it was simply scientific curiosity and everything, but full disclosure, it was primarily driven by commerce, at least back in the day, to have a standard for weights and measures. Because, well, if you're going to trade, you want to make sure you're not getting ripped off and everything. It's like, well, how much grain or barley for this corn, flour? It's like, all right, maybe you have some silver. I have a goat. let's exchange. What is the proper medium? Unless you have a way to really quantify it in a generalized accepted standard, it's going to be very difficult. So, yes, and then we have some of the old references as well, such as hands for horses, feet for football, mod 3, of course, yards. But as human beings continue to spread, interact, barter, trade, we need a common set of standards and measures. So we developed the metric system, and eventually SI became a subset of that. So as we can see here from the little fancy diagram we made, let's make this a little bit small. Okay. So as we can see here, we have the 7 base SI units: seconds, meters, kilograms, Kelvin, Candela, moles, and amperes. And as we can see, I had actually taken this from, I think Dugan had sent me Dugan of the Wolfram Institute sent me a diagram of SI during the summer school. And I remember on NIST's website, the National Institute for Standards and Technology, they had a nice little color wheel for navigating the website. So I'm like, well, let's recreate that. I attempted to originally do it with code. It did not work. So I literally just hacked this together in Keynote, full disclosure. But I wanted to set up in this way because it literally seems like one of those maps you would see in a movie of somebody that everyone thinks is crazy. Maybe they are or aren't, but they have all these pieces of strings and lines going around. So you can just kind of see how everything is together there. So don't worry. I'm not expecting folks to understand everything that's going on here, but if one would like to spend some time looking at it, you have all the listing of everything here, all the different units. In there, we have the abbreviation, so it's not going to take up too much space there. And then it has the physical dimensions here, okay? And solid lines indicate multiplication between things. Dashed lines indicate division, okay? And then you'll have a couple of gray things which are representing dimensionless units. The dimensionless units here are radians and then steradians. So a radian is a unit of angle, okay? Two dimensions. And then a steradian is a 3-dimensional form of angle. So those are dimensionless. Basically, there's no physical representation. Now, I'm not saying they aren't useful, but essentially, these are factors that we use primarily for the Candela here. The Candela, like all the enemies. No, I'm just playing. If you're selling candles, it's probably a useful thing to have. But we're going to make an argument later why you don't need to necessarily have it as a base unit. One of the other things to notice here is we have seconds and amperes, and we're going to get into it because this is a big C here, not a little c for the speed of light. This is representative of coulombs. I'm going to make the argument that we should perhaps include coulombs of electric charge rather than amperes of electric current. And there's going to be a reason why, which if you all stay tuned long enough, we will get to. Okay. As you can see, it kind of makes sense here. All right, you get 2 things of meters, you get meters squared, you get 3 things here. It's probably kind of redundant. You get meters cubed, and you got meters go into the joule, which is the SI unit of energy. It's also got kilograms, and does it have the seconds there? Oh my God, did I do that wrong? Joules has me. Oh, because it's going from newtons, which is going from there and there. Okay. So we've got acceleration, meters divided by seconds there. That leads to newtons. And then newtons is mass, a length, divided by time squared. You add an extra dimension of meters, and then you get energy, aka mass times speed squared. Okay. Fantastic. We're not going to belabor the point because otherwise this will take forever. Okay. So one of the things that's useful about the metric system is because it happens to use certain prefixes and stuff. As we can see, we can express large and small magnitudes, either using deca, hecto, kilo, etc., to express tens, hundreds, and thousands, and deci, centi, milli to express tenths, hundredths, and thousandths. The original way I learned about kilo, mega, and giga was actually from Final Fantasy VII, because of the Bahamut did mega flare. Was it Neo Bahamut did giga flare, and then Bahamut Zero did Terra flare. So I learned from video games those exponential powers, or at least those ones. It's also very useful because it allows us to use base 10. So that makes counting a heck of a lot easier. So as we can see here, we have a little manipulate function. And one of the interesting things, and we'll get to, but a quick note is, coincidentally, the kilogram was initially based on the maximal density of water, which is about 4 degrees Celsius, like 3.98 degrees Celsius, to be a bit more precise, which was equated to 1 gram per cubic centimeter. And then 1,000ths of those grams would give us the kilogram. At least initially, the kilogram was called the grave. Probably not the greatest name, but hey, French Revolution, it is what it is. So initially, it ended up being 1 cubic centimeter of water was 1 gram. And the conventional density of water is still at that. Now it's standard atmospheric pressure. It's a little bit under there, but again, that's more of a Earth-based thing. But I digress. So let's say you had 1 gram. Okay. So we have a single gram. We can do the little counting blocks thing that we learned back in elementary school. So we can go, we got 1 gram, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So we now have a column of 10. And then we got 10, we go 20, 30, 40, 50, 60, 70, 80, 90, 100. Great. We have, at least back when it was defined, we would now have 100 grams. But the kilogram has kilo. That means it's 1,000. So that means we're going to need 10 of these layers. So we've got 100 grams, 200 grams, 300 grams, 400, 500, 600, 700, 800, 900, 1,000. We've achieved the kilogram by historical measure. Cool. All right. Let's go into some of the actual history here as I wet my whistle with a wee bit of coffee. All right. So the second itself, it was based, I'm not going to read through all of this. You can go through here. It's included for those that haven't gone through this. A lot of this is just kind of out of my summer school project, copy and pasted with a little bit of tweaks and everything. So the second started off basically as a literal earthly convenience here. As we can see, it's, well, originally defined as about 1/60th a minute. A minute is 1/60th an hour, and about 24 hours in a day. Yes, an earthly convenience. Now, the interesting part is the concept of minutes and seconds was originally developed in astronomy, because you had some of the Babylonian and Greek folks there. They're gazing at the stars, and they needed to dissect up the sky. So this is where some of our earliest definitions actually came from. Now, how do we measure time? That's something we're still working on. We've got some really good clocks now, hitting like attosecond, like 10 to the minus 18 seconds. Fantastic. Back in the day, what do we have to use? Well, we had some sundials and stuff. A lot of folks are familiar with at least that concept there. All right, the sun's going to be out, but you need to account for like the time of year, because the sun, unless you're on the equator, is going to be a little bit different there. So we use different things, from water clocks, aka water goes drip. You have that there. Essentially an hourglass just using water. And then we're different methods using tanks and everything there. We even use candles, not to be confused with the Candela, because you have a candle of an appropriate length. It's going to take X amount of time to burn through. So sometimes folks will be traveling across the ocean. Maybe you have a compass or something, but you need to know how long you've been going for a particular speed. Hopefully you can measure the speed there, but now you got to relate distance to time, and there are some other methods to go that. We're not going to belabor the point there. It's a fascinating history, units. I would totally encourage anybody that's interested to visit this website and just kind of go through some of the historical documentation. Okay. So over time, we had more mechanical clocks and everything. And basically the pendulum clock developed by Huygens in 1657, it really helped encourage the Royal Society, which is still around today, to help do a contest to basically create better clocks so we could engage in more commerce and more accurately navigate the seas. Again, commerce was a heavily driving factor here. The interesting thing with this is, for time, even just using like the old grandfather clocks, a little tick-tock there, that pendulum had a particular length. So there does seem to be an inexorable relationship between time and length. Just something to point out. And again, we end up having all these extra atomic clocks and everything, blah, 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 using different stuff and things. Long story short is, right now, according to SI, the redefinition, which we have the links here and everything, literally straight out of a manual here, the second symbol S is the SI unit of time. It is defined by taking the fixed numerical value of the cesium frequency, delta VCS, the unperturbed ground state of hyperfine transition frequency of the cesium-133 atom, to be 9,192,631,770 when expressed in the unit hertz, which is equal to 1 reciprocal second. So 1 over seconds. So as we can see here, we have the relationship. And what they're doing, this might come as a surprise, we're literally taking the value of this dimension, and we are literally dividing out the number of oscillations. So basically 1 second is the number of oscillations divided by the hyperfine transition frequency of cesium. So we're taking the numerical value of the hyperfine transition frequency of cesium, dividing it by the actual thing with dimensions itself, and since it's inverted, this is a frequency, we get out time, or second. Okay. So as we can see here, we got, you can query the Wolfram language a little bit. Oh, let's make it a little bit bigger. Okay. So as we can see here, we've got the frequency of cesium divided by that number. We get out this here. When we convert the unit, we get out 1 hertz. Okay. Technically, this should actually be inverted. And we're back. Hopefully I remembered to cut that out. So long story short is, I confused myself there. This should be inverted. So as we can see here, when we have the numerical value of number of oscillations of a cesium-133 atom divided by the frequency of cesium, the hyperfine transition frequency of cesium-133, when we simplify the units, we get out 1 second. Fantastic. All right. Let's move on to the meter. All right. The meter, originally defined as the distance from the North Pole to the equator by root of Paris, divided by 10 million, of course. If you want to talk about an arbitrary basis, I don't think you get much more arbitrary than that. Now, again, maybe there were some reasons for that and everything, because we believe we had an actual measurement for the circumference of the Earth, even though it's kind of more like an oblate spheroid and everything, and it was off a little bit there. But the whole point of this is, even though this basis may be arbitrary, you can pick whatever basis you want, but due to dimensional coherence, you have a coherent set of units, you can pick a basis, no matter how arbitrary, and then align everything else so that it lines up, and you can go back and forth between the different units in a logical basis. Okay. So we'll get to the dimensional coherence and everything. Yes, we're going to do some dimensional analysis and everything, and hopefully prepare folks, either a little review for folks that are more knowledgeable about this stuff. Maybe you'll learn something you haven't heard before, and then for other folks that maybe they're not a professionally trained physicist. And full disclosure, I'm not a quantum mechanic nor a mathematician here. I'm basically an enthusiast, like a lot of y'all, that finds this stuff fascinating. So, yes, there were a number of different ways to go through it. We would do a summation of men's feet and everything to try to have some statistical naturalness or median to it there, but ultimately in 1960, the 11th General Conference in Weights and Measures, the formal definition of the meter became the length equal to 1,650,763.73 wavelengths in the vacuum of the radiation corresponding to the transition between the levels 2p10 and 5d5 of the krypton 86 atom. Whew! Wait a second. It sounds a lot like the definition of the second for cesium. Oh, it almost seems that length and time have an inexorable relationship. Oh, very interesting. Okay, it's now defined by the magnitude 1 over the magnitude of c. Excuse me. Yes. Divided by the unit c. So basically, as we can see here, the meter, symbol M, is the SI unit of length, defined by taking the fixed numerical value of the speed of light in a vacuum c to be 299,792,458 when expressing the unit of M and utilizing seconds from our above definition, where the second is defined in terms of the cesium frequency. Okay. The long story short is it literally ends up being this thing here. And it seems like a weird thing initially, but what's this? This is the hyperfine transition frequency of cesium-133, the numerical value. Then we take the numerical value of the speed of light in meters, and then we swap them. And then we multiply this by C divided by the transition frequency of cesium-133, which ends up giving us this right here. As we can see, we simplify all this jazz, it comes out to 1 meter. Groovy. We continue. And this is a fun one. The kilogram, originally codified as the grave, defined as the mass of 1 cubic decimeter of water, aka 1 liter, at the point where water would begin to freeze, so about 4 degrees Celsius. And coincidentally, as we covered before, this actually related the mass of the kilogram to the meter. So we literally use water to help define our standards. I mean, wouldn't that just beat all? It's how does one get a universe? Just add water. We could only hope. All right. This was done at the behest of French King Louis XVI to help prevent fraud by a commission who suggested what later became a decimal-based metric system. The grave lasted until the French Revolution, and then the gram was adopted. So I have to amend my earlier statement. The gram ended up taking over after the French Revolution. It was adopted as the absolute mass of a cubic centimeter of water at 4 degrees Celsius, so a very similar thing. And then, in 1799, France adopted the legendary kilogram of the archives, which was a 1,000-gram platinum iridium cylinder as the standard. Now, if we take that as the standard, that also means that you would need to replicate that. And then you would need to send this reference kilogram to all the different countries and everything, and well, it happens to be matter, so you want to make sure it's protected and everything, and if there's not really any degradation, hopefully nobody drops it. But again, this could create some issues and everything. So we then ended up having, was it 1875 was where we had the consortium of 17 different countries, along with the US signing the Treaty of the Meter, or the Meter Convention. And this was the official recognition, the International Prototype Kilogram, or the IPK, a thing that you usually see under glass there. It's like some fancy dessert that you don't want to eat. All right. Right now, after the 2019 redefinition of SI, the kilogram, symbol kg, is the SI unit of mass. It is defined by taking the fixed numerical value of Planck's constant to be 6.626 times, 6.626 07015 times 10 to the minus 34 when expressed in the unit joule seconds, which is equal to 1 kilogram times meter squared divided by seconds, where the meter and second are defined in terms of the speed of light and the hyperfine transition frequency of cesium-133. Okay. So long story short is, we take all this jazz. Okay. So now we're doing the same thing. We're taking the numerical value of the speed of light, we're squaring it. We're now dividing it by the numerical value, Planck's constant, not reduced. We got the 2 pi built in there. And then the numerical value for the hyperfine transition frequency of cesium-133. And then we multiply by the constants inverted. We're just doing a little bit of algebra here. And I claim that algebra is awesome. Again, a lot of folks get confused about it and everything. It's maybe not the form that they're most familiar with, but this is how we've defined our current units. So we multiply by the inverted units. We get out this value here and everything. We get out this value, and then we simplify it. And we can see we get 1 kilogram. Great. All right. They're moving along. The Ampere. This is an interesting one because, well, the original definitions, it got changed, and it got changed back, and now we're defining it by elementary charge. As we can see, originally defined as the force generated by a constant current between 2 straight, idealized, basically infinite parallel wires placed 1 meter apart in a vacuum. That came out to be 2 times 10 to the minus 7 newtons per meter. Okay, so, all right, there we go. Newton's force divided by meter. All right. So, as we can see, discovery by Hans Christian Ørsted that electricity and magnetism were 2 sides of the same coin, so to speak, and that putting a compass near an electric current would deflect the needle from magnetic north, helped usher in the paradigm of electromagnetism. Inspired by Ørsted's work, André-Marie Ampere, a French mathematician and physicist, sought to figure out what was going on between electricity and magnetism, and hence why we got this, and the unit, SI unit of current, ended up named after the Ampere. Now, here's the interesting thing. This highlights kind of why standardization is probably a useful thing. During the 1800s, we had basically 4 different systems of current there. So this made things really confusing. Perhaps the best example of this is a more modern one, where we had the Mars orbiter. We sent it to Mars. We sent it there. That son of a gun face planted on the Martian surface. So it didn't really get a chance to do its orbital thing. Why? Well, the calculations were done in meters. It ended up getting programmed in feet. So units matter. Units matter. That was a very costly oopsie. But hopefully we've learned from that a bit there. So we had the Ampere, and then it ended up getting changed. So when it ended up being defined, they ended up using a silver voltmeter, a device with positive and negative terminals that basically you would have a solution of silver nitrate. They would run a current through it, see how much mass ends up accumulating there, and then they would do a calculation. So basically, the deposit running the current through the solution would deposit 0.00118 grams of silver per second from a silver nitrate solution. You might see how that might be a wee bit confusing for folks. It actually got changed back at one point, and now it's defined as follows. The ampere, the symbol A, is the SI unit of electric current. It is defined by taking the fixed numerical value of the elementary charge, so the charge associated with an electron or proton, whatever those may or may not be. That's to be 1.602.176.634 times 10 to the minus 19 when expressed in the unit C, or coulombs, which is equal to 1 ampere second. Okay. Where the second is defined in terms of the hyperfine transition frequency of cesium-133. So again, we are literally taking the elementary unit of charge, dividing by the number of them in 1 coulomb, and then dividing by time, or seconds. Okay. So when the full notation ends up being 1 over, this is the numerical value of the hyperfine transition frequency of cesium. This is the number of elementary charges in 1 coulomb, and then we're multiplying by the transition frequency of cesium times the elementary unit of charge. We get all this jazz. Okay, we got that. We simplify, we get 1 ampere. Beautiful. We're moving right along. All right, temperature. What a fickle thing. We can never seem to agree on the thermostat. It's 3 degrees up, 3 degrees down. It shouldn't really make a difference. It makes a difference for some of us that may have trouble sleeping. Now, what the heck is going on? Now, again, the interesting thing is number of systems often involved using 0 as the freezing point of water. Celsius basically, more or less still does that. Maybe off by like 0.4 degrees or something like that. Maybe that was boiling for water. Essentially, for a deeper dive into thermodynamics, please see Stephen Wolfram's blog over here. All right. So early times or early attempts to quantify temperature. You go back to Philo of Byzantium. He designed a hollow sphere filled with air and water connected to an open air picture. As a rudimentary thermometer, what happens? Temperature goes up, it's going to increase pressure. So, as a reference, you may have, maybe not more recently, but at least when I grew up, we had those little mercury thermometers. So, mercury, hopefully it was sealed well, but behind the glass, but you have a glass thermometer. You put it under your tongue. The temperature of mercury goes up. Oh, look, you're going to have your temperature. And the sheer fact that we did that, potential heavy metal poisoning aside, it seemed to work remarkably well. So it was the same principle there. Okay. So we had a bunch of other methods there, and you had in 1702, Gualmi Amamatons. I completely butchered that. I apologize. I don't speak French. Predicted a minimum temperature of minus 240 degrees Celsius. Anders Celsius in the 1700s originally developed this, and he developed it in kind of an inverted scale, and we kind of just used the flip version of it. And that's where we get the unit Celsius from. So we got better technology and everything. Newton started proposing different things, which was, it's kind of dubious here because Newton proposed 0 degrees to be the freezing point of water and 12 degrees to be the temperature of a healthy human. It's like, It's the 98.6 degrees is generally what's commonly accepted here. And again, some of us run a little bit hotter, a little bit cooler. A little bit of a differentiation here. But it was Lord Kelvin, whom is the namesake of the Kelvin, wrote about it on an absolute thermodynamic scale to first calculate the minimum temperature of negative 273 degrees Celsius. In 1954, the General Conference on Weights and Measures adopted the Kelvin as the base unit for temperature, setting a reference point of 273.16 as the triple point of water, the point where water exists as a solid, liquid, gas, in thermal equilibrium. Okay, even water is again popping up. Is there nothing it can't do? All right, the Kelvin, to our current definition, is the symbol big K, is the SI unit of thermodynamic temperature. It's defined by taking the fixed numerical value of the Boltzmann's constant, K, to be 1.38649 times 10 to the minus 23 when expressed in the units of JK. Just kidding, it's joules divided by kelvins, or energy divided by temperature. As we saw on the board, that's literally what it was. It ends up being technically the Planck energy divided by the Planck temperature. All right. But our modern definition, as we can see here, we're just kind of doing the same thing. We have 1 Kelvin as defined by the numerical value of Boltzmann's constant, divided by the numerical value of Planck's constant, as well as the numerical value of the transition frequency of cesium. Then we invert everything, and we then multiply by the transition frequency of cesium, Planck's constant, and then we divide by Boltzmann's constant. So we're taking the numerical values of the constants, then we multiply by the actual constants inverted. Gives us this number here, and then we get out 1 Kelvin. So as we can see, we've got all that jazz here. We've got numerical value, Boltzmann's constant, numerical value, Planck's constant, numerical value of cesium transition, times all that jazz, and we simplify, we get 1 Kelvin. Great. All right, let me take a couple of moles of coffee before we continue. The mole, moly. Amadeo Avogadro, 1776 to 1856, a lawyer turned chemist, asserted that simple gases were made of molecules. God, I can't believe I missed that. And also theorized the concept of atoms, well, before his time, so to speak, using the term elementary molecules. Originally in honor of Avogadro in the early 1900s, the mole was based on the number of atoms in 1 gram of oxygen. 1971, when introduced into SI, it was renamed Avogadro's constant. Later, it was defined by the number of molecules in 12 grams of carbon-12. Wrong. It's based on the reference mass, the kilogram, which at the time was a platinum iridium cylinder locked away in Paris. The thing you don't want to drop. So we have modern X-ray diffraction technology and everything. And again, I'm not a radiologist. I'm not a chemist. I'm not a professional in this. I just know we're at the point now where we're attempting to use radiometric diffraction to look at silicon, which happens to have a lattice phase structure, to attempt to do counts. That's great. Now, the modern kilogram, again, the whole goal of the 2019 redefinition of SI was to base our units on constants of nature, because hopefully they're not going to be, or if they're going to be constant, or if there is some change, maybe it's like the 13th century. To observers like us, they seem pretty constant. All right. The official redefinition, the mole, symbol mole, the SI unit of amount of substance. 1 mole contains exactly 6.0221407 times 10 to the 23 elementary entities. This number is a fixed numerical value of the Avogadro constant, Na, when expressed in the unit of mole to the -1. It's called Avogadro's number. The amount of substance, symbol N, of a system is a measure of the number of specified elementary entities. An elementary entity may be an atom, a molecule, an ion, an electron, or any other particle or specified group of particles. Okay. As we can see here, this may irk some folks. I know it kind of irked me a bit. 1 mole is defined by Avogadro's number, or the numerical value of Avogadro's constant divided by Avogadro's constant to give you 1. It's kind of a self-referential thing there. Apparently some folks within the chemistry community may have some issues because it does slightly change the old carbon-12 thing. Now, maybe around the 10th significant digit or so, for most purposes, it should be okay. But just, we're going to note that. So we have this value here. So this is literally Avogadro's number divided by Avogadro's constant, which is inverse moles. Well, now you're doing a number divided by the same number that gives you 1. You've got a dimensional unit. And if you've got an inverse of something, if you do 1 over that, it's going to come out to be 1 with the units. Huh. Now you have this other method here, and when you dive a little bit deeper, and I'll probably include this in the finalized or updated notebook included, is that this is for the electron. If you change this, long story short is if you go into Rydberg's constant and you change it to the appropriate terms, because Rydberg's constant has the electron mass in it, as well as elementary charge. So basically, if you divide it by, if you substitute in Rydberg's constant, let's just do this. Rydberg's constant. Okay, let's just get the full definition from Wolfram Alpha. Let's do this definition. There we go. As we can see here, it's got an elementary unit of charge, the charge associated with the electron. It's got the mass of the electron. And if you change this to the proton and then feed it back into this, you're going to get out 1. So that's the whole point of the elementary entities. Because naively, I was originally just like, well, this is kind of weird. And you can also do this if you plug in the Planck charge and the Planck mass here, and then you go all the way through, and you put this together, it's going to come out as 1 as well. I mean, that's pretty fantastic that this works. And the sheer fact that that does work is to help hit home the point that these are coherent dimensions. The Candela, luminous intensity, my old enemy.
My old enemy.
This created a lot of stress for me. Why do I say this? Because this kind of ends up being one of those referential dimensions here. Okay. So looking up here, okay, we have to do the history first. The candela is literally based on the luminous intensity of a candle. If you go to Wolfram Alpha and you type in 1 candela, you're going to get basically the luminous intensity of 1 English sperm candle. I mean, that seems like kind of a crazy thing. But it is an oddity because, yes, we do have dimensions involved, but it is literally defined as an attempt to quantify human visual range. Okay. Now, again, I'm not saying this isn't useful. If you're a candle maker, yeah, this is a very useful unit. Or if you make any type of lighting equipment, yeah, this is a very useful unit. Practically, it is useful. Now, as far as the physical representation of reality, it's basically power with a fudge factor. So let's we had all these definitions here, and then oh god, the first official definition came in 1948, and I quote: Candela was the luminous intensity in the perpendicular direction of a surface of 1/600,000th square meter of a black body at the temperature of freezing platinum under a pressure of 101,325 newtons per square meter, because that's obvious, right? So, so currently, all right, the modern redefinition, because it's so much better. I'm sorry, this irks me. I'm letting my bias show through. I apologize. The Candela, symbol CD, the SI unit of luminous intensity in a given direction. It is defined by taking the fixed numerical value of the luminous efficacy of monochromatic radiation of a frequency 540 times 10 to the 12 hertz, or the big K sub Candela, or to be 683 when expressed in the unit lumens divided by watts, which is equal to the Candela steradians divided by watts. Okay, so steradians, so we've got solid angle here, or the Candela solid angle divided by kilograms, meters times seconds cubed, where the kilogram, meter, and second are defined in terms of HC and the hyperfine transition frequency of cesium. Upon looking here, you may see why an individual like me might have a kind of a problem. It's like the Candela is defined by, wait a second, wasn't this part of the original definition? Wait a second, we've got this, and then we've got this. It bothered me. Now, this ends up being a self-referential definition. And again, this is literally a fudge factor here, because they're estimating basically that particular frequency, which is within the, that's like 5 times 10, it's basically about 5 terahertz, I believe. Yeah, billions, yeah. So it's basically about 5 terahertz, the frequency of light in the visual spectrum of humans, and that 1/663 is about the human visual range. And again, we're all different, but this is why it kind of irks me for some things. So as we can see here, if we put in all that jazz here, we're literally doing 1 divided by the numerical value of Planck's constant, times the frequency of cesium-133 squared, that's 683 factor. We multiply by the frequency of cesium-133 squared, then Planck's constant, and then that other term, our K sub CD over here. Okay. After all that, we get out 1 Candela radians squared, or 1 Candela for 4 pi steradians. So basically, 4 pi radians is, 4 pi steradians is solid angle. So basically, you have a light bulb, assume a perfect sphere. Let's assume a spherical cow light bulb. Radiates equally in all directions. That would be 4 pi steradians. Cool. All right. We've gotten through the history. Fantastic. Coherent units. Here's where things get fun. Coherent units. What's the point? All right. And again, this was first brought to my attention from, again, this is just cut out from Wikipedia, where it may or may not remain. Dad had showed me this first. Basically, with these relationships, we have a coherent set of units. And again, a lot of us have heard F equals ma, force equals mass times acceleration. Cool. But if we extend that to energy equals force times distance, as well as power equals energy divided by time, we then have a coherent system of units. And some folks may have heard the old expression, once you have F equals ma, you can basically recover all of physics as we essentially know. And again, caveats here and there and everything. But the reason for this is force equals mass times acceleration. All right. It's a mass. That's a distance. That's all divided by time squared. Yeah, and another distance. Oh, now you have two distances. And you get energy equals mc squared. You get a mass, and then you get speed squared. And then power is literally just energy divided by time. So it's that energy over a period of time. Now, here's the thing. Why the heck should you care about this at all, especially with all like the repeated algebra and everything? Now, again, as we established earlier, the whole point is once you establish a reference base, then you can construct your unit system so that everything you can kind of go between them utilizing a coherent or logical system of units. Okay. Now, again, as we say here, F equals ma, you can derive all of physics. And again, you should have your doubts about any all-encompassing statement. But one of the things where if we're looking for the underlying machine code, as in the Wolfram Physics project, or as Professor O'Tooth may say, the rule for our world, you're going to probably want to have some logical coherence in whatever system you construct. Let's just take a moment. Let's break this down. Let's have a good old example that I had from the Wolfram Summer School last year. Let's say you have a clothes dryer. You'll want to dry your clothes. We're not going to worry about any of the thermodynamic drying or anything at this point. We're going to assume a spherical cow, i.e., we got a cylinder. All right. So let's say you give it a poke. All right. You have some force. All right. So you can get that dryer drum to start to rotate a bit. Okay. So you've got a force and cause that dryer to accelerate. Okay. Now, one little nudge isn't really going to do that much there. Again, it would depend upon the force of the nudge. But ideally, if you want a working clothes dryer, you're going to want that acceleration to continue. And you're going to want that force to travel a distance. So I give a nudge, but that force ends up having the dryer rotate. Oh, you've completed a cycle. And that uses energy, because energy is force times distance. Now, again, thermodynamics aside, but if you want your clothes to actually dry, you're going to want that dryer to continue to spin. So you're going to want to have that requisite amount of energy divided by time. So that's where we get power, which is energy divided by a period of time. So kind of like this laptop is using energy right now. If I rip out the plug, it's going to switch to battery, and I'm only going to have so much power I can draw before this just shuts down. Okay. So again, that's just an instance, and we have a nice little manipulate tool here for the dryer drum example here and everything. Yes. Thank you, Wolfram Notebook Assistant and ChatGPT to help me work with the code and make it a lot faster rather than having to do everything by hand. Okay. So we got the drum mass at just 1 kilogram. We got the drum radius here. We got some acceleration. So let's move forward by time steps. So as we can see here, we got that. All right, we go forward 1 time step, 2 time steps, and go, yeah. And we can fully go through here. Here, let's get the little animation. Let's slow it down a wee bit so we can get to the point. All right, a little faster. All right, so as we can see, over time, this is going to rotate here. All right. I mean, that's neat and everything. Now we could also do the could have the angular acceleration, which is essentially going to do the same thing because acceleration has time in it. So as we can see here, essentially doing the same thing, just as our example, because we give us a little nudge, we got our force. That force travels a distance, and that distance is, once we complete a cycle, we're going to want that to continue, so we're going to divide it by time. So again, there's just a little rudimentary tool here, and so basically it's showing the relationships. And down here, we can see energy, power. Oh, look, 1/2 of the energy. It kind of sounds like 1/2 mv squared or something. That's very fascinating. And then we go up to 2. So as we can see here, they're 2 seconds. So we're going to require 2 joules in this spherical cow scenario. That's 1 unit of power because it's gone an additional second. Now it starts at 1. It's full disclosure there. But if we continue on, you're going to notice it's going to be that ratio. Once we go up to 4, okay, it's going to take 2 watts of power, but that's going to be the equivalent of 8 joules over 4 seconds, which we have here. Cool. And again, it's just a fun little tool you can play around with, but it's basically just going to show you the total sum of different things. You're going to see the time, you got the rotation angle and everything in there. It's showing the total distance, it's showing the amount of energy, and since basically it's all using ones, it makes it a lot easier. Now, in the real world, we don't really have spherical cows. Again, that's an idealized scenario, but it's basically an exercise to help prime one's mind to what's going on. All right, as we can see here, let's go back up to our larger stuff. Okay, by now, the reader and the viewer are probably thoroughly confused about all the spinning stuff doing all these interrelated things. Don't panic. The whole point is to just communicate that there are these relationships and they seem to magically work. Now, again, this has taken millennia of human ingenuity and observation in order to figure out what's going on in a coherent manner like we do now. But if we see here, if we just take energy, which was our friend up here, it was the middle one, energy equals force times distance. Okay. Now, the interesting thing is these are just using Planck units because these are the ones of our world. The elementary units, or the limits of reality is probably a better term. The limits of physics as we know it, because they're not always the smallest thing. Planck time and length are the minimum according to physics as we know it. Planck mass, charge, and temperature, those are unit limits. And we'll get into that a little bit later here. But if we just see here, there's just energy. If we divide energy divided by time, and we get power. And since they're Planck units, it would be the Planck power. All right, really big number. Energy times time gives us the dimension of action, or angular momentum. So we can see it's represented by h bar. Now, if we take energy and we divide it by length, we're going to get out force, because, force times distance, or a length, gives us energy. So we can go back and forth, see? Huh? All right, and then energy times a length is going to give us something that, unless maybe you're in deep into physics, you might not be aware. I wasn't, but h bar c, and that's the bending stiffness of space-time itself, apparently. The interesting thing is bending stiffness is the exact same as the Newtonian gravitational constant, except the Planck mass, rather than being downstairs in the denominator, is upstairs in the numerator. All right. It's actually something you can see, because if we go back up to our constants, what we got here? We've got the Planck mass is defined as the square root of h bar c divided by big G. Well, h bar c is the same dimensions as big G, except the Planck mass is downstairs. Since the Planck mass is downstairs and then being divided, that means this whole thing comes out to the Planck mass squared. Hence, we take the square root and we get the Planck mass. Just something useful if folks aren't familiar with it. Again, plenty of folks are, and I'm sure this is just a review, but hopefully even the experienced among us might be able to take something interesting out of this talk. So, all right, let's go back down here. All right. So the whole point of this is to demonstrate once you have a coherent basis of units and the logic holds, we can go between these different units to do different calculations and relate them to our actual measurements of different stuff, things within our world. Cool. Now the power of dimensional coherence. So the claim is the real superpower, so to speak, comes from the fact that these simple rules allow us to parameterize the different stuff that's doing things in our world in a logical relationship. And we're going to go through the actual definition that they have here in SI, straight out of the booklet over these dimensional powers. So as we're going to see below, any unit that you raise to the 0th power. So if you raise it, okay, something normally just to the 1st power. The 1 often is not shown, but if you raise it to the 0th power, that gives off 1, a unit of 1 that is not explicitly stated. And below it's going to tell us that 1 is the neutral set to any system of elements. So again, the link is right here. So this is from the redefinition of SI from 2019. Base quantities are mentioned using SI. So got our base qualities here, time represented by T. And again, this you can argue over some of the notation here, but we got time, length, mass, electric current, thermodynamic temperature, amount of substance, and luminous intensity. All right. All other quantities, with the exception of quantities that are number of entities, are derived quantities, which may be written in terms of base quantities according to the equations of physics. The dimensions of the derived quantities are written as products of powers of the dimensions of the base quantities using the equations that relate the derived quantities to the base of quantities. In general, the dimension for any quantity Q is written in the form of a dimensional product. So basically, within SI, whatever dimensional unit with physical stuff you can write using these things. So basically, you're taking time, length, mass, electric current, thermodynamic temperature, number, so that's moles, and luminous intensity. Sorry, it's the Candela always another story. So basically, and then you have these superscripts here. It's alpha, beta, gamma. God, I don't speak Greek, but basically, you have these representations, and you can raise them to powers, and then you could have whatever numerical value it might be according to our measurements. Our detector goes click, we do calculations. Fantastic. Now, the beautiful part is all these superscripts are typically small integers. You usually don't get more than, I don't know, it's 3, 4, maybe 5 for your exponent. So that makes things much simpler. Now we should note, there are quantities Q for which the defining equation is such that all the dimensional exponents in the equation for the dimension of Q are 0. This is true in particular for any quantity that is derived as a ratio of 2 quantities of the same kind. For example, the refractive index is the ratio of 2 speeds, and the relative permittivity is the ratio of the permittivity of a dielectric medium to that of free space. Such quantities are simply numbers. The associated unit is the unit 1, symbol 1, although this is rarely explicitly written. Very often the 1 is silent. So this is something to keep in mind. Now note, there are also some quantities that cannot be described in terms of the 7 base quantities of the SI, but are quantities that are a number of entities. Example are a number of cellular or molecular entities, or degeneracy in quantum mechanics. These quantities are also quantities with a unit 1. Now, note, we're talking about quantities. It's going to go into an argument very shortly about the mole and counting, but I digress. The unit 1 is the neutral element of any system of units, necessary and present automatically. There is no requirement to introduce it formally by decision. Formal traceability to the SI can be established through appropriate validated measurement procedures. Cool. Okay. And again, we can see this with a little manipulate function. I got to make this smaller to fit. All right, there we go. Okay. So again, you start with whatever your reference is. Get a reference of 1 here. All right. Now, you can adjust these, so you can adjust time to be whatever it wants. So you could either increase this, and this will increase them all, or we just, let's keep it at 1. 1. There we go. You could increase the time, but for this case, let's just look at these numbers here. So if we were to have different exponents, so we can see. We got time. Let's do the easy one. Just do it time to the -1. So as we can see, we got our base quantity. We've got 1 for length. We've got -1 for time. All right, it's gonna give us out speed, but we could adjust this a little more. That's keeping track of our dimensions there. We can go down another 1 for that. Okay, so we got 3 dimensions there, and then we could add a dimension of mass. We do a -1. All right. So now it's keeping track of our dimensions just like we had up there. I realize this isn't the nicest. I should probably update this before at some point to update this because it is a nicer calculator. We're not gonna dwell on it. Now again, at this point, the reader or viewer should now actually be thoroughly confused and probably should take a break. And again, take your time.
A new nation where we choose our own laws.
Here, said sir.
Choose our own leaders.
Yes, sir.
And choose our own systems of weights and measures.
Don't panic. As myself, I've spent much time confused, and it is a reoccurring state that happens. Every time I redo this, I either confuse myself and or I learn something new, hopefully the latter more so. But that's part of the exercise. That means one's mind is actually processing and trying to grok, so to speak, what's going on. Let's get to the payoff. Computationally reduced SI, aka the art of noticing. The fact that we can actually reduce our 7 base SI units down to 5 doesn't mean we should give up on the units. Like if you're buying Candela's type of light, yeah, you're going to want to have Candelas and everything. But the claim is our physical dimensions of measure, the ingredients of reality themselves, we can computationally reduce them, so to speak, to 5. Time, space, mass, charge, and temperature. So if we take a look here, here's our original little SI wheel. Okay. Now, it's going to get a little bit wonky here. Now, first, before we discard any units, one of the things I learned from Stephen Wolfram is before you cast aside anything, you might actually want to know what's going on. So the Ampere versus Coulomb. So the first thing that we should note is the Ampere is literally defined as charge per second. We take Coulombs, we divide it by seconds, simplify, get the Ampere. Okay. As we saw before, the Ampere is currently defined as elementary charge divided by the number of elementary charges in 1 Coulomb divided by seconds. So what this is telling us that by definition, It's elementary charge, the amount in 1 Coulomb divided by seconds. Or SI unit of electric current, the Ampere is in this case a derived unit from the elementary unit of charge and the second. So as long as we have charge and time included in our computationally reduced system, we can derive current. As we can see, it's literally coulombs is amperes and time. Okay. Fantastic. Okay. Moles versus counting. All right. This is one of the things where I kind of go back and forth and everything. Now, again, I'm not saying you get rid of the unit. I'm just saying if we can count, it might kind of be a moot point. So the mole, again, a very useful term in chemistry. Ain't no doubt about that. But again, the definition is a numerical count of entities or the amount of a particular type of stuff, so to speak. All right. And again, when it's literally Avogadro's number divided by Avogadro's constant that just has inverse moles affixed to it, it's going to come out to be what? Okay. Great. Now, again, it's a count. As we saw from the earlier definition, which is right here, there are also some quantities that cannot be described in terms of the 7 base quantities of the SI. But they are quantities that are a number of entities. Number of entities? Well, this is a measure of number of entities. So one may have a count of something, and they might represent it by numbers. Maybe 1. The number of things that you could include as a count of a set. So it kind of is right there. But again, the mole is a useful thing. I'm not going to take the mole away from anybody, but effectively it is a numerical count. So again, I would claim that we can count. Move on. The Candela. So as with a mole, I'm not saying it's not useful. Again, any type of light, like the lights and everything that's going on, causing a little blur on the board behind me, having an actual measure for a human-related thing makes a lot of sense. But when you take this crazy definition that has self-references in it, again, I almost wanted to say, I think I may have, at one point, I think I maybe agreed with ChatGPT. I mean, like, oh, isn't this circular logic? And I'm like, that seemed a little strong. And he came back and it corrected me. It's like, well, it's self-referential logic. I'm like, that's what I was thinking. But I wanted to get at the Candela a little bit due to my own personal frustration. And again, it's self-referential. It's literally humans eyeballing it. And it also has a dimensionless term, which is solid angle. Okay. But as we can see too, based upon the current and the previous definitions, in both cases, scientists were literally eyeballing it. Again, useful, yes. Fundamental for computing the stuff and things that go on in reality? Mechanically, it's just power, because the dimensions itself. All right, so mass, a length squared divided by time squared. That's cubed, I understand that. But mass, speed squared divided by time, it's power. Because energy divided by time is power. Groovy. All right. Moving right along. Okay. So now we're going to get to the payoff. The benefit of computational reducibility. Now we're going to take a look at an absolutely crazy flow chart. It's similar, but this is actually literally a flow diagram that actually does have code for it. Again, thank you, Wolfram Notebook Assistant and ChatGPT for helping me out with this. God knows I didn't want to have to program everything by myself, and it actually kind of seemed to work now, but let's, all right, there we go. So as we can see here, it's basically the same thing as our above diagram, except it's not in the wheel form. However, everything should work out. So basically, solid lines involve multiplication, dashed lines include division. So first off, we've substituted the Ampere, the SI unit of electric current, for the Coulomb, the unit of charge. All right. And since we have seconds here, we have charge divided by time gives us 1 ampere. Great. All right, we've recovered the ampere. Now, one of the things you need a mole for is the katal, which is 1 mole divided by seconds. But mole, we just have it as a dimensionless count. We can put it in there. All right. Then our other dimensionless units, we have radians and steradians here, units of angle and solid angle, respectively. Okay, those are dimensionless, and again, it's hard to have a notion of angle unless you're comparing two lengths, at least. So you kind of need length to derive angle, so you kind of see where this is going here. Got our meters involved in all this jazz. We got seconds all over the place. We got kilograms. Now, one thing to note, temperature is technically not included to anything. We'll get to that in just a moment. But as we can see here, these lighter red things here are basically the Candela, the Lumen, and Lux over here. Now, dimensionally, that's what they include. They include kilograms, meters, seconds, and then kilograms and seconds over here. Okay. Now, again, you can apply some solid angle, but these are the actual dimensional, physical dimensional ingredients involved there. As we can see here, joule, we got meters, we've got time, and then we've got mass going in. So we got mass, and the mass up there, and then 2 units of meters, and then we've got a dashed line for seconds because it goes in the denominator, or it says 1 over seconds. Watts is, okay, we got a solid line for meters. Right, we got kilograms, we got dashed line showing that seconds is in the denominator. And you can follow this through. And again, it omitted like meters squared and meters cubed because that's a little redundant there and everything. Okay. I'm not expecting folks to understand this in one fell swoop, but we're gonna continue. So as we can see, the ampere is clearly related directly between charge and time, like we see. Replacing the mole as a dimensionless count, we can recover the katal, or the cat. The Candela and related units in light red are related by the dimension of power and already include the dimensionless units of angle, radians, and steradians. As we can see, the Kelvin, it ain't actually attached to anything. WTF, mate. Again, this should be glaring, but if we notice our original color wheel and we look over there, the Kelvin literally only linked to the Kelvin. It wasn't actually attached to anything else. Why don't we just scrap temperature altogether? So perhaps the most pragmatic reason is because this is a parameter we measure all the time, pun intended. Literally, like you go to CERN, how are we measuring a lot of the stuff that's going on? We get ginormous calorimeters. They are measuring thermodynamic temperature. Hey, like many things we have, your engine's got a thermostat and everything. Why? You don't want it to overheat. It's measuring temperature. So temperature is essentially a bridge between thermodynamics and energy using Boltzmann's constant. Because remember, Boltzmann's constant over there, it's energy divided by temperature. So if we have the ability to determine a temperature and we have other parameters, we can actually go through and compute what's going on. Now, one may bring up the sheer fact that utilizing the logarithm of the total number of microstates available to a system may sound dubious, as is this not just simply counting as with the mole? In a way, yes. However, experimental evidence leveraging the ideal gas law has shown this apparent statistical magic appears to be true, or at least to observers like us. So that's a pretty fantastical thing. And also, if how do you measure all the energy of things? Now, you might have the mass and E equals mc squared, but how do you measure the movement of individual little stuff? Well, we got to kind of aggregate, and if there are a limited number of microstates, and this seems to work, beautiful. That's why temperature is included. Because as we can see, it's literally is just the bridge between energy and temperature. Big in this. All right. So 1 joule divided by Boltzmann's constant. All right. Gives us a quantity. So 1 joule would be the equivalent of 7 times 10 to the 22 Kelvin. That's really hot. Now, again, we can take that temperature and then multiply it by Boltzmann's constant. And we get 7 times 10 to the 22 Kelvin again. But we can simplify. Oh, excuse me. When we go through and we do the calculation, we end up getting out 1 joule. Okay. So, oh, that's, okay. Because it's Kelvin times Boltzmann's constant. You simplify, and then you get out 1 joule. See, this is why I prefer seeing K sub B. It makes it a little bit more clear. All right. So again, this is why Boltzmann's constant acts as a two-way bridge between energy and temperature. Perhaps there's a better way to parameterize what's going on. I don't know of one. I'm open to suggestions. All right. Copy as we computationally reduce coherence. I digress. All right. All right. Computationally reduced coherence. Finally, we're back to where we started. Armed with a new computationally reduced toolkit to try to better figure out what the heck is going on. The true goal here is to help the viewer better understand how units work and to use this knowledge along with other tools such as Mathematica Notebook, Wolfram Alpha, or many of our LLM friends to help move humanity forward. So as we can see, we have our 5 constants of nature, which when combined in particular forms, we can get out Planck units of those 5 bases. Okay. So let's get a little table here. Let's get rid of that code. So as we can see, we can arrange them as we did earlier. We can get the Planck time, get our G, our H bar, our C. Okay, we got different values. We got time, length, mass. Note for charge, it's the only one that doesn't have a big G in it. It also has 4 pi in there, which is interesting. And some folks will argue about that. And note here, depending on one's convention, some may remove the 4 pi term from the Planck charge. Okay. We also have the Planck temperature over here, and we continue. All right. So one of the reasons why I'm noting this is just full disclosure. It's important for computationally reduced SI. I would claim that we should include the 4 pi there. Why? Because as noted a little bit earlier, the effective forces of charge and gravitation unite at the Planck scale. So if we take Coulomb's constant of proportionality, following Q1 times Q2 divided by R squared. So this is your thing times another thing divided by R squared. So your inverse square law. When we happen to take Coulomb's constant, multiply it by the Planck charge squared, divide it by the Planck length squared, get out this really big number, 10 to the 44 newtons. That's force. Newton's gravitational constant of proportionality follows a similar schema where you got mass 1 times mass 2 divided by r squared. We have Newton's gravitational constant. We got the Planck mass squared divided by the Planck length squared. Oh, we got 10 to the 44 newtons. So at the limit of physics as we know it, both constants unite at the Planck force, which is 10 to the 44 newtons approximately. Great. The other reason, and this is probably a stronger argument, our dynamics. All right. The fine structure constant is the squared relationship between elementary charge and the Planck charge. Now, we can see from the fine structure constant alpha, it is a dimensionless relationship between the elementary unit of charge squared divided by 4 pi, speed of light, the electric constant, and h bar. Okay. So by definition, this is the fine structure constant. You can see it's all that jazz is right there. Now, coincidentally, one may notice that this is a dimensionless number, meaning that the numerator, or the dimension of charge squared, must be canceled out by a dimension of charge squared because it's a dimensionless number. And we have a thing with a unit, whatever unit it might be, if you divide it by the same unit, whether it's big or small, the units cancel out. That's the magic. And you will get a dimensionless ratio. So if the top number in our numerator is elementary charge squared, that means the denominator must be charge squared. What charge is that? That's the Planck charge. So we take elementary charge squared, divide by the Planck electric charge squared, we get the same number. So what that means is this whole thing is charge squared, which shouldn't be a surprise because this 4 pi c epsilon naught h bar. We go back up here, 4 pi epsilon naught h bar c, the square root of that, the Planck charge. Now, it's explicitly there, literally, like within the definitions, but this is something that actually a lot of folks don't really seem to be aware of. So again, this is a little tidbit. If this helps at all, great. If it's review, hopefully you can still get something useful out of this. But we continue. Now, here's part of the argument for this. Now, this relationship is pretty straightforward, but again, it's not often discussed. As this dimensionless number is one of the greatest mysteries in physics, any insight on why this may be the case may help us better understand what's going on. Professor Feynman poetically riffed upon this. There's a link, and I think it's from Cargo Cult Science. There is a most profound and beautiful question associated with the observed coupling constant E, the amplitude for a real electron to emit or absorb a real photon. It is a simple number that has been experimentally determined to be close to negative 0.085424455. My physics friends won't recognize this number because they like to remember it as the inverse of its square, or about 137.03597. with about an uncertainty of 2 in the last decimal place. So it is actually 2 more nines there. It has been a mystery ever since it was discovered more than 50 years ago, and all good theoretical physicists put this number up on their wall and worry about it immediately. You would like to know where this number for coupling comes from. Is it related to pi, or perhaps the base of natural logarithms? Nobody knows. One of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. We might say the hand of God wrote this number, and we don't know how he pushed his pencil. We know what kind of a dance to do experimentally to measure this number very accurately, but we don't know what kind of dance to do on the computer to make this number come out without putting it in secretly. Well, that's my argument. Part of an appeal to authority. So this is one of the primary reasons why I would claim that a computationally reduced SI perspective helps make these relationships much more clear. Now, again, doing a similar thing as we done earlier. All right, let's just take time over here. Let's just look at the bottom. So basically, if we were to adjust this, again, we're scaling the unit, but we're just changing whatever the value of the second is. So if we were to change the value of the second, we were to make it 1,000 times greater, the only thing it's going to do is it's going to shift the exponent another 3 magnitudes in the negative direction, because it's a very small number. Remember, negative exponents end up kind of making it small, whereas bigger ones usually make it bigger. Okay. So again, you can feel free to play around with this. What I found most interesting was, so if you drag all these things over, you can see these numbers here. So if we go up by, we're going up by a factor of 1,000. So if we notice what happens is we are now scaling this. So we've gone up by a factor of 1,000. Yeah. And the gravitational constant has gone down by 6 orders of magnitude. It's gone down by 3. Speed of light goes up by 3 because, well, length divided by time, if you're going to make time 1,000 times greater, well, your speed of light is going to change, right? Because we're scaling it by this. Because time is in the denominator, and if we're changing it by 3 orders of magnitude, which is the Planck time, the speed, you can think of it minimum unit of length, Planck length, divided by a minimum unit of time, you get Planck time, you get that out. Now again, you can play around with this all you want. What I find interesting is we max all these things out. All right. Long story short is everything goes back to where it was, except the elementary unit of action, h bar. Gravitational constant's back to the negative 11th power, speed of light's back to the 8th power, the electrical constant is back to the minus 12th power, and Boltzmann's constant is back to the minus 23 power. However, the 6 orders of magnitude change from negative 34 to negative 40 for h bar there. Why? It's kind of threw me off for a little bit, but okay. The reason why is if we look at numerators versus denominators, gravitational constant, we've got 3 dimensions in the numerator, and we've got mass and time in the denominator. 3 dimensions. So if we go up by 1,000 for a dimension of length, we go up by 1,000 for each of these, that's going to cancel out. Length and time, if this goes up by a factor of 1,000, this goes up by a factor of 1,000, it's going to stay the same because you've got a numerator going up and a denominator. We look at the electric constant, we have 2 dimensions in the numerator. We got these negative exponents, so that means there's, we got 4 dimensions in the numerator. We got 4 dimensions in the denominator. And for Boltzmann's constant here, we've got mass and length in the numerator. We've got time and temperature in the denominator. So those 3 units in the numerator and denominator are going to cancel out. We look at the dimension of action. We've got mass times the length, but we've only got 1 dimension of time in the denominator. So that's a 3-to-1 relationship. So if we go up by 1,000, it's going to go up by a factor of about 1,000,000, because that's 6 zeros. I thought that was a pretty neat thing. So again, feel free to play around with this yourself. All right. Now, let's get into a little bit of Wolfram Physics, shall we? There's some speculative work for parameterizing units in the Wolfram Physics project. I'm begging again. So methodology in Wolfram Physics. And a lot of this was from my summer school project and a little bit rehash, so to speak. So last year, I had the opportunity to attend the 2025 Wolfram Summer School. And the project I was assigned was units, to develop a history and potentially find some method to attempt to more formalize the unit system, because they have some estimates based upon the age of the universe. And we're going to get into a hack. I'm just going to call it that because it is a hack that seemed to be able to replicate the original values within about one order of magnitude. Completely different method. Very, very dubious, I claim. So one of the things that got stressed to me during lunch, basically around my mid-project meeting, Xerxes, the organizer of the physics branch, stressed the idea of energy and momentum having a strong meaning within our graph structure. And Professor Wolfram assigned me additional reading and homework. And upon doing the homework, I came upon this passage. So anything we directly observe must ultimately have a signature in the causal graph, and a potential hypothesis about energy and momentum is that they may simply correspond to excess fluxes of causal edges in time and space. Consider a simple causal graph in which we have marked there, blah, blah, blah. So upon doing some homework, we looked at this, and I'm like, this passage was very interesting. So I had used another attempt to try to quantify things. I was off by 17 orders of magnitude. It didn't really make sense. At one point, I think Stephen got up and started pacing around the room. People were like, oh my God. I'm like, he sits a lot of time. He needs to walk and everything. Who cares? But as we can see, we have over here, in standard quantum mechanics, in effect, h bar through energy equals h bar times frequency. But in reverse, this relationship, E, is a measure of energy, not the energy associated with a single causal edge. And to convert between these, we know in effect the number of states in the branchial graph associated with our quantum frame, or the number of nodes in our current slice through the multi-way system. We will call this number G. All right. Essentially, G is a scaling factor used to determine the claimed elementary units, such as time and length, for the Wolfram Physics project. And they do this by taking this as just a dimensionless number and taking the square root and taking this as a square root and dividing it into Planck units. So long story short is we did some calculations, and upon noticing this little part where it said excess fluxes, I did a calculation from what I already had, and I returned something in a notebook after I read that. I'm like, I looked at the dimension that I got out that I wasn't familiar with, that I had done after Xerxes had given me that information, and the dimension that popped out happened to be flux. I noticed this number. You could view it as the Planck flux. So basically, I took the Planck intensity, which is the maximum energy flux. I divided by the Planck energy, and you got this. So it's flux energy rate per area energy unit. Long story short, it's 1 over the Planck length squared and the Planck time. Okay. So this is a dimensional number. So, but the thing is, it was very close to one of the original numbers estimated from the project, which, as we see over here, they went with the number basically about 10 to the 116th power. They're going through, they're calculating this, and as you can see, they have it this K term, or this kappa term, as 1. So they go through, and they're using, I think that's a Somos quadratic reoccurrence formula and stuff. So long story, they're estimating utilizing the age of the universe, or the Hubble time, and as you slowly increase this factor, it goes up. So basically, this factor of 10 to the 112, I just happened to notice, well, exponentially, this is 10 to the 112. It's kind of close. What if I do the naive thing and just literally divide out, or in this case, multiply by, because it's in the denominator, meters squared times seconds. So we get this unit out as a dimensionless number. So the claim is it's a Planck spacetime cell count and a given hypersurface area as a scalar. Now, there's a philosophical argument that could be made that if our hypergraph structure is literally underlying medium for flux, then maybe we could take this dimensional count as it is. If we're looking for flux, and this is the Planckian dimension of flux, maybe it makes sense. Again, very dubious. However, if we take this and we use this as our G term, we take the square root of that, so we raise it to the 1/2 power, we multiply it by the Planck length, we get about 10 to the minus 92 meters. Coincidentally, it's within about 1 magnitude from the initial physics project estimates. Seemingly remarkable thing is it's completely different. Because as we can see here, this was originally calculated, the Hubble time, divided by the elementary unit of time, times this term, and then our kappa term here. Now again, if you want to see more detailed explanation, feel free to check out the links below. But now we have this logarithmic plot, and this is essentially within the ballpark of the Wolfram Physics estimates. So that's why I wrote literally it's within the ballpark. And again, this is most likely a simple numerological coincidence. Occam's razor would say the simplest answer is probably true. But if we continue to compute it, we get about 10 to the minus 100 seconds. For energy, we get about 10 to the minus 29 electron volts. And again, this is literally a giant hack. So the only reason why I ended up actually following this is the seeming, quote unquote, ability to replicate the original physics project estimates by another methodology. However, if we're going to consider energy as momentum as excess fluxes of causal edges in time and space, perhaps there is some notion of the dimension of flux. And I didn't identify that. I only knew just because Wolfram Alpha said dimensional interpretation, flux. Thank you, Wolfram Alpha. So as we can see here, we have what was returned using this hack versus the original estimates. So original estimates 10 to the 93 meters. We get about 10 to the minus 92. Elementary time, about 10 to the minus 101, 10 to the minus 100, and so on and so forth within about 1 magnitude. Now, this shouldn't be really surprising because, well, these are all scaling Planck units by the same number. So according to dimensional coherence, they're all going to be, if one is within about 1 order of magnitude, they should all be within 1 order of magnitude because it's being scaled by the same number. Okay. Now we should also note this doesn't always make sense because for something like the Planck power, it ends up returning a value that we know is not a minimum because it's larger. Then again, the Planck power in itself is one of those Planck combinations, but there isn't a square root. So that's interesting and an area open to further investigation. And again, this was basically a hack. So at least for logical inference, and I'll just read this, the methodology behind this is to identify features of physics as we know it, to verify the underlying rule of the world. We should be able to count edges, at least within Wolfram physics, to determine the associated energy and explore a multi-way system to identify other standard phenomena. One such method was inspired by one of my mentors, Hatem, as well as Nick, would be to simulate the formation of a black hole, because we have general relativity, we can have a Schwarzschild black hole, or we could have a Kerr black hole, rotating charge, all that jazz. But if we have knowledge of that, we could start mapping edges, and we could try to do a count and model this. Maybe we could see if there's some there. Maximum entanglement speed, this is a fun one. So again, the following result is nothing new, but simply something that I noticed from the given definition within the Wolfram Physics project. It also allowed me to create this fun little image of a maximally entangled observer, aka Stephen Wolfram, with a little double cover of a hypergraph going behind and in front of him there. So we got our zeta equals elementary energy divided by elementary time equals the Planck power. Okay. What the heck does this mean? So basically, while I was trying to come at this from multiple angles of attack, so to speak, they had this original estimate. So maximum entanglement speed is 1 over the elementary time. And then you scale it with your g here, and then you could have elementary energy divided by the elementary unit of action, h bar, and then it would equal blah, 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 blah. So basically, it gives you a frequency. So that frequency, when converted, is about 5 times 10 to the 99 hertz. Ginormous number. Or we could express the maximum entanglement speed, this zeta term here, in regards to the associated energy with edges in the causal graph as elementary energy divided by elementary time. Okay. Long story short is an elementary energy divided by elementary time. So a minimum of energy divided by a minimum of time is going to give you the maximum power. Now, again, this is not just because we happen to guess this G term, this little crazy term here correctly. This is because we have a coherent system of units here. So as the Planck energy divided by the Planck time will always yield the Planck power no matter what we choose to scale it by, as long as it's the same magnitude for both. Why? Well, we go all the way back up to our little coherent unit structure. Way back here. All right. Because remember, power is just energy divided by time. Oh, okay. So all I did was really just state what was already there. They just used just the exponential powers just for quick calculations and everything. And I just looked at that number. Oh, that looks familiar. Oh, it's the Planck power. Or at least, where is it? Okay. Here we go. Or it's very close within the rounding error because that's what it is defined as. Cool. Now, one of the things said there was, how could this actually be a power there? And at one point, they're talking about potential astronomical events, maybe like a supernova or something. For reference, how much power the Planck power is. If we took the mass energy of what's believed to be the supermassive black hole in the center of the Milky Way galaxy, it's about 4 million solar masses. Okay. We take that and we convert it to energy. So 4 million solar masses times c squared divided by the Planck power. Basically, this would be output the mass energy of Sagittarius A star in 21 seconds. That's crazy. Because it puts out 1 Planck mass times c squared. So 1 Planck energy per Planck time. It's about 10 to the 44 Planck times in 1 second. That's a lot of energy. And then you're doing that, yes. That's why it's such a ginormous number. That's a crazy term there. What could potentially be doing that? I cannot say. Get into space and time like hypersurfaces. Okay. So as we can see here, it's brought to us from MathWorld. A generalization of an ordinary two-dimensional surface embedded in three-dimensional space to an n-1 dimensional surface embedded in n-dimensional space. A hypersurface is therefore the set of solutions to a single equation. We got this here. Okay. So that's cool. Now, if we learn that a hypersurface is an n-1 dimensional surface embedded in an n-dimensional space, looking at our Planck flux, which we're using to scale the G term, that scalar term that we're dividing the Planck units by in Wolfram Physics, we find that we have 2 dimensions of space and 1 dimension of time. Seems very convenient. If we live in a 3 + 1 dimensional space-time, then by our previous definition, it seems to constitute a hypersurface. All right. So let's take this dimension of Planck flux and multiply it by its equivalent energy. Okay. So it gives us this ginormous term over here. This ends up being the Planck intensity. I got that from Wolfram alpha. And let's do this for momentum. If we take the Planck flux, multiply it by the Planck momentum, oh, we get the Planck pressure. Under pressure. Oh, that's the maximal limit of pressure as we know it, that if you were to hit, essentially you would create a black hole. Why? Otherwise, we're going to exceed the limits of reality. Almost like space-time is, not error correction, almost like error prevention built in. Thanks, space-time. As we can see, we return the Planck intensity and the Planck pressure. These are maximal states for a given Planck volume. If we were to actually achieve this energy momentum, yeah, we create a black hole. So these correspond to the limits of energy or momentum within a minimal system. In this case, the Planck scale. Within Wolfram physics, this could be seen as the maximal number of causal edges crossing a space-like hypersurface in regards to momentum and maximal number of edges crossing a time-like hypersurface. So one of the ways I tried to, when I first heard about this, it kind of reminded me of something I saw for the Bessel function. Let's play this right here. All right. So this is often associated with forms of dispersion. It's kind of like a drum head and stuff. You can see it can vibrate there. So you're almost going to view the flux as the stuff going out or versus stuff going in for a particular surface. Okay. Now, this is an area for future investigation, and we mention it here as one of the first things that came to my mind personally. Another way one may try to conceptualize this is that we can rewrite our unit of flux from inverse time and area to frequency area, aka 1 over the Planck time, and the Planck length squared would be equivalent to the Planck frequency divided by the Planck length squared, or the maximal frequency divided by a minimal area. Cool. Now, while this might be trivial, it might help observers like us make better sense of what's going on. So the question still remains, at least if this is an interpretation of a minimal physical unit such as the Planck volume, through Planck's through space and time like hypersurfaces, why does it correspond so well to our estimated position in the multi-way system in regards to Wolfram physics? The simplest answer is it's just a coincidence and has no true meaning. It's Occam's razor. All right. The alternative immediately raises a plethora of questions. Why is there any apparent correlation? Does G change our scaling factor? If so, because if G is initially the position we are, the number of computational steps or so in a hypergraph-based system, but if things are going to keep expanding and everything is going to get bigger and bigger, that number is going to change. However, if we use that number to scale all the different units, would we even notice? I brought that up to Professor Wolfram. It's like, yeah, probably should need some more formulation on this. Now, and again, his main goal, to my knowledge, is just to find rules that satisfy him to show what's going on. The technicalities are usually up to other folks that come to the different summer schools or summer research programs, and other folks that are interested to continue the work. I just happen to be interested in the units, and apparently I was the first person since the initial formulation to just kind of take a look at them. I ain't no genius or anything. I just look, what is this? Oh, okay, that's kind of cool. Now, again, probably just a coincidence. All right. So, but if we were to take this literally, if that G term was literally the magnitude of the Planck flux, that has a defined ratio. But what does that mean? Does that mean we're in some maximal state right now? Perhaps a state of equilibrium, whatever that may or may not mean? How the heck could something we intuit as a minimum have any correlation to a maximum? These are interesting questions for future research. Alrighty then, we're almost there. The basis of stuff doing things. All right, here's where we get the payoff, where you can actually attempt to do scientific stuff and things, or at least see relationships, and heck, who knows, maybe you'll discover your own, something maybe that we missed. But the power of one. Congratulations, you've endured the computational logic presented, and now, as said, it's time for the payoff, so to speak. The benefit of thinking in Planck units is that they are literally the limits of reality as we know it. Now, again, a lot of times you'll hear, oh, the Planck units, they're the smallest things. Now, within conventional physics, the Planck length and Planck time are minimums. However, the Planck mass, the Planck charge, and the Planck temperature, on a unit basis, long story short, is if you were to cram those into a Planck volume, you're basically going to create a black hole, because you're going to exceed that maximum energy density per unit. Now, again, a kilogram is like 10 to the 8 Planck masses, but you can't cram it down into a Planck volume. There, it's much more macroscopic type thing. But what these actually are, these are constants of proportionality setting the physical limits of reality as we know it. And I would claim using them can help us get a better intuition for what the heck is going on. Let's take h bar, for example. Basically, Planck's constant divided by 2 pi for that cycle per second. All right. Now, rumor has it, Max Planck originally came to that as a kludge. Basically, it's like, you have the ultraviolet catastrophe. What's going on? It doesn't seem to work. There seems to be a Wien peak there. And then the Rayleigh gene's like, it doesn't seem to be working. So it's like, all right, what would we need to insert to solve this ultraviolet catastrophe? He came up with about 6.6 times 10 to the minus 34 joule seconds for Planck's constant, the non-reduced one. Okay. It ended up taking several years later before more folks deduced that and started to figure out, oh, look, this seems to actually be a useful thing, because it had the dimensions of angular momentum. That's why you'll hear spin very often. But now, since h bar is a constant of proportionality, let's play around. So if we take h bar, we divide it by the electron mass times the speed of light. All right, we convert that. We get this number here. What the heck is that number there? Oh, that happens to be the natural unit. A natural unit? Well, natural unit of length, as we can see here, because it's literally h bar divided by the mass of the electron and the speed of light from CODATA. All right. Now, if we take that unit and we multiply it by the fine structure constant, we get this number here, which corresponds with the classical electron radius, as we can see here, because it's literally the definition. And then, instead, if we were to divide it by the fine structure constant, we return the Bohr radius. Fantastic. And again, these are things that a lot of them I didn't know off the top of my head. I mean, I took modern physics for like a week in college and stuff, but I needed to drop it for another class. But I spoke with a professor, and I was able to do some of the homework. Why? Because it was interesting. Because one of the other things that I heard from Stephen Wolfram is you have to be interested in something. If you're not interested in something, you're not going to do it. I am an excellent example of that. I apologize to all those that I've let down. All right. So how you can query nature. The whole goal of this computational essay in Core 1 entry is to help imbue the viewer with the power to investigate reality themselves. Again, I've utilized the power of the Wolfram language to help discover many of these relationships that we as humanity have taken literally thousands, if not potentially millions of human years to figure out what's going on. So, for example, if you're playing around with constants like the electric constant and magnetic constant, charge and magnetism seem to go together like a horse and carriage. But you end up getting out this number here. What is this? I don't know what this number is. Okay, maybe it's basically the mass per energy conversions, the relativistic. If you put a mass in that and you swatch it to kilograms, it'd be the relativistic mass of 1 joule. That's not the point of this, but if we look at this, all right, it doesn't really make sense. Let's invert it. We can do 1 over. So we go from a really small number to a really big number. But now the units start to make sense because we got meters squared divided by seconds squared. Where have we heard that before? Oh, meters divided by seconds is speed. It's speed squared. And since it's in Planck units, if we take the square root of that, oh, look, we get the speed of light in a vacuum. Fantastic. We've discovered what James Clerk Maxwell did over 150 years ago. But again, I believe this is also the reason why you have practice problems and homework and stuff, because again, you can put all this into a large language model and you can get out this, that's fine. But sometimes doing it step by step gives one a bit more of an intuition. And again, other folks, my mathematician friends would point out, it's like, oh, you're still using a calculator and stuff for that. You should do it by hand. I'm not going to argue with my mathematician friends. They're much smarter than me. However, if you're going to use the computational tools we have available, why not? Because this could actually help better formulate better questions for your large language model agent or whatnot there. And sometimes you might want to double check, because sometimes listen, we all make mistakes, including our agent friends. So I'm just putting that out there. Now, since we're getting to the end of the video, God, I have no idea how long this is going to be. I apologize. Be wary numerology. So my claim is numerology until it explains more with less, i.e. Occam's razor. Now, many of us, myself included, enjoy playing around with numbers, attempting to find something fundamental that is yet to be noticed by others. Scientific discovery. Tools such as Wolfram Alpha are not simply a dimensional calculator, although the Wolfram knowledge base has about 10,000 or so units of measure, probably the largest database to my knowledge, but it also shows a relationship between other potentially relevant things. So if you see a comparison between things and you're like, that's about 137th this thing. Maybe you multiply by the fine structure constant, and that's going to be what happens, which you would notice from these earlier calculations for the Bohr radius. Because if you just take a look at that, let's just do this. Equals h bar. No, we need to do double. H bar divided by electron mass C sent to Wolfram Alpha. Okay, it shows this. It shows this. Oh, look. It's about 137th the Bohr radius. So with a bit of knowledge, one could intuit. Maybe you multiply by that and you'll get that. Now, again, these are established relationships, literally by definitions, but it provides additional context for yourself and all of us to try to figure out what's going on. And that's essentially the whole point of this exercise here. Earlier, we went through an example from the summer school project I did trying to find a relationship within Wolfram Physics. And we were utilizing the Planck flux as our scalar. Okay. Now, again, that's just a crazy thing. That was just basically pattern matching. Oh, this number seems to fit. This happens to line up with some of the words that I heard and everything. Let's see. Oh, it seems to replicate things. Now, the methodology is completely different. And again, most likely, it's just a coincidence. But if there was something deeper, it takes somebody smarter than me to try to figure out what's going on. But when we start looking at what's happening here, so for instance, if you were to just put this into Wolfram alpha, you may get out the Planck intensity. It doesn't always do it. No, it's not perfect, but the ability to see the relationship between the different things in our world, I think that's an incredibly powerful tool, because when we're multiplying that unit of Planck flux, or 1 over the Planck length squared times the Planck time, and we multiply by the Planck momentum, we get the Planck pressure under pressure. So the issue that we run into is we literally did the naive thing. And again, this is a major problem, as our chosen system of units should not matter.
It doesn't matter!
Once you choose a basis, you line up everything else, as we saw with some of those calculators and little tools you can play around with. Everything needs to be coherent by that F equals mass times acceleration, force equals mass times acceleration, energy equals force times distance, and power is energy divided by time. As long as you have that, the unit system shouldn't matter, because constants in nature, by definition, they're going to be the same. Now, the numerical value may change, but the relationships will hold as long as you have a coherent system of units. That's why doing the naive thing, oh, let's just divide it by the dimensional units. That literally is crazy. And it's even worse. It's the claim that there exists a quote-unquote preferred frame. Now, again, from our friends at Wikipedia, take it for what it's worth. In theoretical physics, a preferred frame or privileged frame is usually a special hypothetical frame of reference in which the laws of physics might appear to be identifiably different, simpler, from those in other frames. In theories that apply to the principle of relativity to inertial motion, physics is the same in all inertial frames and is even the same in all frames under the principle of general relativity. Now, aside from the earlier use of the density of water that linked the kilogram and meter, and the triple point of water used to substantiate the initial value for absolute zero, there should be no link between our reference unit and reality other than by definition. All right. So now we're literally at the end of the video. Let's let down our hair, so to speak, and buckle up as we conjecture ahead. So, frame of reference. Let me take a look here. In physics and astronomy, a frame of reference or reference frame is an abstract coordinate system whose origin, orientation, and scale have been specified in physical space. It is based on a set of reference points defined as geometric points whose position is identified both mathematically with numerical coordinate values and physically, signaled by conventional markers. An important special case is that of an inertial reference frame, a stationary or uniform moving frame. For n dimensions, n+1 reference points are sufficient to fully define a reference frame using rectangular Cartesian coordinates. A reference frame may be defined with a reference point at the origin and a reference point at 1 unit distance from the origin along each of the n coordinate axes. Again, I'm not a quantum mechanic, but that sounds like, okay, you got a Planck length as an elementary building block. You can go out in the different dimensions. You could square it to get an area. You could cube it to get a volume. Maybe that's completely wrong, but my intuition is that kind of makes sense. Okay. So let's entertain the absurd claim. If the absurd claim of a preferred frame was the case, we'd expect to see similar cases from other numerological coincidences representing flux through the causal graph utilizing numerical value of Planck flux as a scalar. Again, why might that be the case? I don't know. Maybe does that help solve reality? Again, probably just a coincidence. So let's do the naive thing with some particles and stuff. And let's take the electron. It's a really small mass. Let's divide it into the kilogram. We would get a dimensionless number because the kilogram is reference 1. So we do the naive thing again, and we square the kilogram, and we divide by the electron mass. We get this big number, which it's a little over half the mass of our sun there. So it's approximately around a little above the mass below which stars undergo convection through their mass itself. So basically, it's kind of an average M-type star. Okay, a little bit smaller than our sun, but okay, that doesn't really jump out. Let's do the same with a proton mass. Kilogram squared divided by the proton mass. Okay, we get a big number. It's about 100 times the mass of Earth. Or about 1/3 of Jupiter, something like that. All right. Now here's a fun one. Let's try the Z boson mass. Kilogram squared divided by the Z boson mass. It's about 10 to the 24 kilograms, which it's kind of close to the mass of Earth. Now, again, this is a fun coincidence. It's not really the greatest argument. So a more fun one that I'm personally a fan and very biased about is the hierarchy problem. So what is the hierarchy problem? Again, from Wikipedia. More technically, the question is why the Higgs boson is so much lighter than the Planck mass, or aka or the grand unification energy, or heavy neutrino mass scale. One would expect the large quantum contributions to the square of the Higgs boson mass would inevitably make the mass huge, comparable to the scale at which new physics appears, unless there's an incredible fine-tuning cancellation between the quadratic radiative corrections and the bare mass. Doing some quantum field theory here. Again, not a quantum mechanic. The problem cannot even be formulated in the strict context of the standard model, for the Higgs mass cannot be calculated. In a sense, the problem amounts to the worry that a future theory of fundamental particles in which the Higgs boson mass will be calculable should not have excessive fine-tunings. So let's take a look at this relationship, see if we can notice anything. All right, Higgs mass divided by the Planck mass. Okay, the difference, or the hierarchy problem, it's like 10 to the 17 orders of magnitude difference. That sounds like a problem. All right. Since the dimensions of mass cancel out, we get a dimensionless number. Not very intuitive, aka we got a 17 order of magnitude problem. So let's look at the squared relationship. Got the Higgs mass divided by the Planck mass all squared. Simplify, you get 1.05 times 10 to the minus 34. So those that have done perhaps many calculations, often punching into a calculator, may recognize these first couple of digits in magnitude. It looks very similar to one of our constants. When we look at the numerical value of h bar, we get 1.05 times 10 to the minus 34 joule seconds. Now again, this might match, but there's some dimensions attached there. What's going on? Now again, this seems completely crazy, as one is a dimensionless number and the other has units. But if we were to continue down this road of madness, we could do our numerology so that we take the square root of the elementary unit of action. Again, we're doing the same thing. We're dividing by the reference of action, the joule second. We're taking the square root of that. We get 1.02 times 10 to the minus 17. 1.02 times 10 to the minus 17. So long story short is, if we took that, we then multiply it by the Planck mass, we're going to get pretty good agreement with the Higgs mass. Now again, some more recent measurements have shown it a little bit lower, about just over 125 GeV, like about 0.05, maybe 0.2. If you follow this out, it ends up giving a very specific prediction, which is 125.376-ish giga-electron volts, where the uncertainty comes from the Planck mass. So we only have that to like 5 significant digits because gravity is involved. Now again, while this may replicate the magnitude of the difference between the Higgs mass and the Planck mass, utilizing our reference unit of 1, you have to be really careful there. Could there be something deeper? Perhaps we should be more conservative in our wild speculation. Because again, I can say that, But then again, we are instantiating that there is a preferred frame. And again, in order to validate this, you're probably going to need about an additional 2 significant digits for the Higgs mass. Okay, it's a very difficult thing to do because we're comparing all these things, the relationships between the Z boson, the W boson. When you actually go through, then you've got the Weinberg angle, and you go through all these calculations. And the speculative thing, it would be amazing if it was true, but can I claim that this is fundamental reality? I'm going to err towards the professionals and say, oh, this is a quirky thing. Now, if we get the Higgs boson to 7 significant digits with extraordinarily low error, and then it seems to match, okay, now you have more of an argument here. But 3 significant digits, to be fair, for a long time, we thought the speed of light was 3 times 10 to the 8 meters per second. So for that period of time, we had 0 significant digits correct. It was actually 299, 2.9978 times 10 to the 8 meters per second. I always forget the last couple of digits there. So you have to be careful. Before you jump off the edge, you're going to want to have a large amount of statistical data, and that's why you have particle colliders and stuff to collect enormous amounts of data to see what's going on to the best of our ability at the time. Okay. We could take this crazy conjecture and expand our numerology to literally the next level. So how will we do this? Well, let's take the Higgs mass energy and then turn it into a spherical cow. Okay, so what do? We literally are going to take the mass energy of the Higgs and divide it by 4/3 pi r cubed, where our radius is the associated Higgs-Compton wavelength. Okay, we do that calculation. I get this ginormous number here. So this is an energy density, like 5 times 10 to the 42 in kilograms divided by meters per second. So, or pascals. It's a pressure, under pressure. So again, let's relate this to the measured vacuum energy density of our universe. What do we get? 1.08 times 10 to the minus 52. Incredibly small number. Now, this looks a little similar to something else within cosmology. We look up the cosmological constant, lambda. It's about 1.1 times 10 to the minus 52. Again, same problem. It might be close, and again, it seems to be, and depends on which, according to some other dark energy surveys and stuff, maybe it's actually larger. So again, we don't know. More precision is required, and perhaps a better understanding about what's going on. But then again, there's no units. It's just a dimensionless number. Okay? So what the heck is going on? So let's take a look as part of the calculation for the cosmological constant. It includes the Einstein's kappa constant, which is 8 pi divided by the Planck force. Okay. We take all this jazz, then we multiply it by the Einstein C4 constant. Okay. Coincidentally, we get out just over 1 inverse meter squared, which the cosmological constant is per meter squared, so it's inverse meter squared. Well, here's our missing unit. So again, this is essentially our missing unit for the cosmological constant. Does this mean we can claim, oh, yeah, it's obviously this? Now, again, there's a lot more that goes into, because it should technically be the Higgs vacuum expectation value, which is about twice the Higgs mass, roughly there. So it's like we would need to reformulate so much stuff on a speculative result. Now, again, I would love for this to be true and be something fundamental. Why? Because I'm a narcissist. I love being right, but can I claim this is with absolute certainty? No, I can't. And again, one of the things I've learned from Stephen Wolfram is before we throw out what we know, we should probably have a really good reason for it. And with the Wolfram Physics project, he's claiming that there are reasons why he's going in a particular direction. He has these tools and things are making sense to him and some other folks, and fantastic. I don't want to take away anything from anybody else, but I'm just looking for interesting coincidences that maybe we're not normally looking at. And this is why I'm showing you all this, because you can just play around and maybe you'll get lucky. Maybe you're just much smarter than myself. And once you intuit how to use some of these computational tools and everything, you'll be able to figure out what's going on and perhaps find the rule for our world. So again, now you also just don't want to do one thing. You want to look at an entire spread of things. So we have a little chart here that uses this whole quote unquote spherical God Cow conjecture. What is this? We're doing the same thing with the mass energy and the associated Compton wavelengths of these different particles. And as we can see, the Higgs falls right around about 1 meter for this reference here. Because if you take the square root, yada, yada. And again, it's I think the input was probably slightly different. I did this a little while ago. But if you're looking at the weak sector, W boson mass, it's about 2.5 meters. Z bosons, about 2 meters. The top quark, using this formulation, would be about 0.5 meter. The Higgs happens to be the one that falls right around the meterish range. Why might that be? Well, I think it needs to fall within that range or else we wouldn't exist. So does that mean it's fundamentally tied to the meter? I mean, personally, I would love to have 10 significant digits defined for the Higgs mass, because maybe this would be a good way to use the meter, because it seems to be pretty dang close. But again, these units are for human convenience, so we can better try to figure out what's going on. It just happens to fall around that range. And again, while this is all fun, we must be careful to not extend our claims. Okay, so that's that. It's been a heck of a time. God, I still got to edit this down, and I only have so much time left because I am such a procrastinator. So before we finish with this, let's do a little bit more fun. So what we can do is, I still have a little bit of room left on the board. Let's utilize it. What can we do? Let's take a look at space-time. All right. Yeah. Space-time. Whatever that may or may not be. Okay. So we got space-time. Might have a better marker here. All right. So utilizing what we've covered here, let's take the limits of reality. What is space-time? We live in a 3+1 dimensional space-time. Cool. So if we were to write that out in Planck units, it would be the over here. We'll do the Planck length. So we'll do L sub P, and that's cubed. And then T sub P, that's time. All right. So we have 3 dimensions of space, 1 dimension of time. But space-time is where we live. So space-time is an embedding. So that would mean it should actually be 1 over the Planck length cubed times the Planck time. However, since algebra is awesome, we can rewrite this. We can rewrite this so it goes to F sub P, which is the Planck frequency, because frequency is inverse of time, L sub P cubed. So that would mean that space-time could be viewed as a frequency volume.
There's a phrase that I heard you say with Einstein. The general view is that he spatialized time, but instead what we should do is temporalize space.
Right.
I don't know about you, but that seems to make a whole heck of a lot more sense to me. Huh. This is something I didn't know about and stuff. I probably looked at these numbers before. I actually learned this from a mad scientist named Rick. Not that Rick, the other Rick. So, hence why within my Wolfram summer school project from last year, the last person credited was a Mr. Rick DeWitt, mad scientist, because, well, he's the one that shared this with me, and I used some of that intuition to attempt to match and replicate results from the Wolfram Physics project within one order of magnitude. Highly speculative, but I mean, this is what it is. So hopefully we're able to take something away after God knows how many hours this was, but with that said, I'm tired. I'm going to a monastery. Peace out, everybody.
Oh, there goes gravity. Oh, there goes gravity. Choke. He's so mad.